Good evening and welcome. This is Padma Shri Dr. S.R. Valluri Memorial Lecture Series. It is scheduled on all Saturdays. Timings evening 6 p.m. to 8 p.m. as per Indian Standard Time. This program is a virtual program through Zoom. All are welcome irrespective of their geographical locations. Thanks to Corona for having made this possible. The topic for discussion for the Zoom meeting on today, the Saturday, 15th January 2022 from 6 p.m. to 8 p.m. as per Indian Standard Time is a continuation of the chapter on thick cylinders. Learn free from any place. Learn free at any time. Learn free at any pace. This is an Atmanirbhara Bharata initiative. The program is called as lecture series. However, wherever possible, discussion method will be utilized to the extent possible for exchange of ideas among the participants, including the speaker, for the purpose of encouraging everybody in terms of thinking, learning, problem solving, and understanding the topic of interest. The resulting multiple points of view is expected to help to build better knowledge, understanding, and interpretation of the topic discussed. The chapter is on thick cylinder. Welcome viewers. This is the 6th session of the Padma Shri Dr. S.R. Valluri Memorial Lecture Series, which is held on all Saturdays from 6 p.m. in the evening to 8 p.m. in the evening as per Indian Standard Time. The topic for discussion today is thick cylinder. It is, you can call it as part 2. Actually, thick cylinder is a topic, or strictly speaking, it is a small portion of a topic in the subject that was popularly known as strength of materials. The subject is nowadays renamed as mechanics of solids. It is taught in engineering colleges and polytechnics, which was a common subject in those days for all branches of engineering. For reasons not known, this subject that was popularly known as strength of materials was experienced by the majority of the students as the most difficult subject to study or understand. However, this is not true. In reality, it is one of the easiest subjects to learn, easy to remember, easy to practice, and easy to score highest possible marks in the qualifying examinations. What is actually needed is that the student is required to study only 62.5% of syllabus prescribed for the course of study in engineering colleges and polytechnics to obtain 100 out of 100 or 100% marks in the qualifying examinations. This is because of the simple reason that in all examinations, the students are asked to answer only 5 questions out of 8 questions given in the question paper. In some university examinations, they will be asking students to answer any 6 questions out of the 10 questions given in the question paper. 5 questions to be answered out of 8 questions given in the question paper in most of the universities and our institutions just means that only 62.5% of the prescribed syllabus is sufficient enough to obtain 100 out of 100 marks. Answering just 3.5 questions out of 8 questions correctly, clearly, and completely ensures a first class getting greater than or equal to 60%, which just means the study of 43.75% of prescribed syllabus is sufficient to obtain a first class in the qualifying examinations. The thick cylinder is called thick if the inner diameter of the cylinder is less than or equal to 20 times the thickness of the cylinder. In this sketch, it is shown D subscript I as the internal diameter, D subscript O as the outer diameter. The difference between outer diameter and inner diameter is equal to 2 times the thickness of the material. So, if the diameter which is measured inside is less than or equal to 20 times the thickness of the material, then that cylinder is called as a thick cylinder. Di is inner diameter of the cylinder, Do is outer diameter of the cylinder. Now, knowing the diameters, it is easy for us to calculate what is the inner radius and outer radius. Inner radius is half times the inner diameter. Outer radius is half of the outer diameter. Here we will use 2 items. One is called Px. It is called radial pressure at any radius x from the center of the cylinder. Similarly, Fx is used to identify hoof stress at any radius x. In solving problems on thick cylinders, we make use of what are known as Lamb's equations. The Lamb's equations are Px is equal to B by x square minus A and Fx is equal to B by x square plus A. The important thing to be noted in this one is this is not like the formulas that we use for calculating, say, area of a circle, perimeter of a circle, diameter of a circle, given the radius, or like that. There, area of a circle means we use A is equal to pi r square, where r is the radius of the circle. Or A is equal to pi d square by 4 if d is the diameter of the circle. So problems of that type do not require any brain at all. They are blindly, we can substitute the value of what is the data that is given and calculate what is required using the formulas. For example, if radius is given, you can find the diameter. you can find the perimeter, you can find the area of a circle using the standard formulas. The Lamb's equations in that fact are slightly different. These are the general form of equations for giving the distribution of the radial stress and the tangential stress or the hoop stress with respect to distance x from the center of the thick cylinder. Now, for each problem, it is necessary to evaluate knowing the given information in the problem, the values of A and B for every problem we solve. They are not the same value for all problems. So therefore, the job is first to determine the values of A and B, which are constants for that particular problem. The values are determined from known conditions which are given in the problem. Radial pressure is compressive and hoop stress Fx is tensile. So usually tensile stresses are treated as positive and compressive stresses are treated as negative. Now what we have to do is substitute known values of Px, that is the radial pressure, and or Fx, that is the hoop stress. Either the values may be given in the problem or some of them may be assumed as needed. Once we substitute these values in the Lamb's equations, the constants A and B are determined to obtain the Lamb's equations which are applicable for the given particular problem. Example, a particular problem, the Lamb's equations Px is equal to B by x square minus A and Fx is equal to B by x square plus A can become something like Px is equal to 82051.3 divided by x square minus 3.2. Fx is equal to 82051.3 divided by x square plus 3.2. In this example, value of A is 3.2. It is in M.B.A. In the value of B in these equations, in this particular example, is 82051.3. It is in newtons. So once we determine the Lamb's equations to the particular problem, then we can keep on varying the values of x on the right hand side of the equation by giving different values of x starting from x is equal to Ri, that is the inner radius of the cylinder, up to and including x is equal to Ro, which is the outer radius of the cylinder. And we can take convenient steps of increment so that we will get sufficient problems through points through which we can draw a smooth curve. So we can choose any increment I for and determine the values of Px and Fx for different values of x. So once the values of Px and Fx for different values of x are obtained, then they can be tabulated. In this example, I is the increment in x. So we can have a column. First column, we can write different values of x, example in millimeters. Second column, we write the radial pressure Px, which is in MPa, and Fx is the hoop stress, which is also in M.P.A. So for various values of x, the Px and Fx values are calculated from the Lamb's equations which we have obtained for the particular given problem. So the values of Px and Fx obtained for each values of x, what we have selected in column 1 are given in column 2 and column 3 respectively. So here each value of Px and Fx corresponds to the corresponding x value. It starts from the inner radius 100 mm and goes up to outer radius 160 mm. In this example, the increment or step size is taken as 10 mm. Any convenient increment size can be selected so that we will get sufficient points or sufficient values for Px and Fx so that it will be convenient to draw the smooth curve passing through all these points. Example, the values which we have obtained in the table are plotted here so that we can show the results graphically. The value of radial pressure Px, which is at the inner radius, is given as 5 MPa. At the outer radius, it is not specified. So we will assume when nothing is specified on the outer surface, there is no external pressure acting on the surface. Therefore, the radial pressure at radius equal to RO or outer radius is taken as 0. The Px value at the inner radius is 11.4 MPa. It decreases to 6.4 at the outer radius. From the graph, it is seen that Px, the radial pressure, and Fx, the hoop stress, are maximum at the inner radius Ri, and Px at R0 is 0, which is assumed as explained earlier. Maximum shear stress is given by Fs max is equal to 0.5 times Fx minus Px. However, Px is compressive and therefore it has a minus sign. So minus of minus will become plus. So it is necessary to add the value of the hoop stress and the radial pressure and take half of the sum or the average of these two values. So it is calculated here as 8.2 MPa at radius or I, that is inner surface. So same formula we can continue for all x values and find the arithmetic average of the radial pressure as well as the hoop stress, which gives the variation of the shear stresses with thickness of the cylinder. Now we will consider a example. A metallic pipe of thickness 60 mm has an internal diameter of 200 mm. It carries water under a pressure of 5 megapascals. Determine the maximum shear stress and the maximum and minimum intensities of circumferential stresses induced in the pipe material. Show the variation of the radial pressure and the hoop stress across the thickness of the pipe. It is important to remember that the circumferential stress is also known by different names like tangential stress or hoop stress or tensile stress, and they are treated as positive. Similarly, radial stress is also known as radial pressure. It is compressive and it is treated as negative. The shear stress is half of the algebraic sum of the radial pressure and the hoop stress at any radius x from the center of the pipe. So, since Px is negative, though we write Fx minus Px, numerically we'll have to add them and divide by 2 or multiplied by 0.5 so that we get the average of these two values. In this problem, the data given is one is the thickness of the pipe, which is 60 mm, and di is the inner diameter of the pipe, that is given as 200 millimeters. Once these two values are given, it is easy for us to determine what is inner radius of the pipe. It is half of the inner diameter. So 200 divided by 2 will give 100 millimeters. Now RO is outer radius of the pipe. It is equal to inner radius of the pipe Ri plus the thickness of the material of the cylinder. Now outer radius of the pipe is, from the given data, 100 plus 60. 100 is the inner radius, 60 is the thickness. So added together, the outer radius of the pipe R naught will become like 160 mm. Once we know the outside radius, taking twice of that, we get the outer diameter of the pipe, which is 320 mm. Now in this problem, we want to find what is the maximum shear stress, maximum tangential stress or hoop stress, minimum tangential stress or hoop stress or circumferential stress. And we want to show the variation of the radial pressure Px, the hoop stress Fx, and the shear stress Fsx with change in x values. So the Lamb's equations are x is any radius from the center as shown in the red color in the sketch, any point at a distance x from the center of the pipe. A and B are the constants which are to be determined from the data given for solving a particular problem. So the values of A and B will be different usually for different problems unless we get the same data. So in this problem, the known conditions are, one is the radial pressure at the inner surface, that is when x is equal to 100 mm, that is inner radius, is given as 5 MPa. The external pressure is not mentioned in the problem, but whenever that information is not given, it is general practice to assume that the external pressure applied outside the cylinder is 0 at the inner radius. So the constants A and B are to be determined using this information given in the problem. And since there are two constants, we need at least two equations out of the four that are possible from the Lamb's equations which are given. So Lamb's equations Px and Fx we can apply at inner radius, we can apply at outer radius. So for each inner radius and outer radius, we get two different equations for radial pressure, two differential equations for hoop stresses. So in this problem, we will substitute Px is equal to 5 M.B.A at x is equal to 100, that is in the first formula. Similarly, we apply Px is equal to 0 M.B.A when x is equal to 160 mm or outer radius in the same formula. So we will get two different formulas for each one of these conditions. So when you substitute 5 MPa for Px and x is equal to 100 mm, then we will get 5 is equal to B by 100 square minus A. So once we get 5 is equal to B by 100 square minus A, which you can call it as equation 1, then we will also apply Px is equal to 0 MPa when x is equal to 160 mm or outer radius, which is assumed as 0 in this problem because there is nothing given information related to the external pressure acting on the given cylinder in the problem. So therefore, 0 is equal to B divided by 160 square minus A. This becomes the equation 2. Now, if we subtract equation 2 from equation 1, 5 minus 0 will give 5, minus A and minus A will cancel, and then B by 100 square minus B by 160 square will be there. Now, taking B common factor, we can write 5 is equal to B into 1 by 100 square minus 1 by 160 square. So 5 is equal to B into, if we take LCM, denominator will be 160 square multiplied by 100 square, and the numerator we will get 160 square minus 100 square. Now the numerator is like A square minus B square. So this can be factorized and written as A plus B into A minus B. So 160 plus 100 will give 260, and 160 minus 100 will give 60. Therefore, we can write 5 is equal to B. In the numerator, it is 260 multiplied by 60, and in the denominator, it is 160 square plus 100 multiplied by 100 square. So rearranging the terms, B is equal to 5 into 160 square plus 100 square divided by 260 into 60. So after calculating these values and simplifying, we can write a value of B as 82051.3 newtons. Now substitute this value of B equal to 82051.3 newtons in the equation 2, which is 0 is equal to B by 160 square minus A. Then rearrange A taking it to left side, you will get 0 is equal to 82051.3 divided by 160 square minus A. So therefore, A is equal to 82051.3 divided by 160 square. So on simplification, value of A becomes 3.2 megapascals. Substitute values of A and B in the Lamb's equations, which gives A is equal to 3.2 MPa and B is equal to 82051.3 newtons. So on substituting, the Lamb's equations for this particular problem become Px is equal to 82051.3 by x square minus 3.2. Similarly, hoop stress Fx is equal to 82051.3 by x square plus 3.2. Now, substituting different values for variable x in the right hand side of these Lamb's equations, starting from x is equal to Ri or inner radius up to and including x is equal to Ro or outer radius in increments of I. Generally, we take equal intervals value for I. The values of Px, the radial pressure, and the hoop stress effects for different values of x are obtained or calculated. These results can be written in the form of a table that is shown here. So values of Px, the radial pressure, and Fx, the hoop stress, for different values of x, starting from Ri is equal to 100 mm up to and including Ro, or radius of the outer surface, is equal to 160 mm, are shown in this table. From the table, it is easy to see that both the radial pressure and the hoop stress, they are maximum at the inner radius Ri equal to 100 mm, where the radial pressure is 5 MPa and hoop stress is 11.4 MPa. The shear stress at any radius is given by the equation as explained before, keeping in mind that Px is compressive, that the radial pressure is compressive. Therefore, though in the formula we write Fx minus Px, it will become numerically added, and it is the average of the values given for radial pressure in the second column and the hoop stress given in the third column. Now, these are added, that is Px and Fx are numerically added and the sum is divided by 2. The result is the shear stress at different radii. They are given in the column number 4. So that is, in the first column, if you take 5 MPa and 11.4, add them, it becomes 16.4. Divided by 2 or multiplied by 0.5. So that you will get that 16.4 divided by 2 or multiplied by 0.5 is 8.2. Similarly, all other values of the radial pressure and the hoop stress are added and the sum is divided by 2, which is written in the fourth column with the title FSX, means shear stress at radius x. This is in MPA. From the table, it is seen that the radial pressure Px, the hoof stress Fx, and the shear stress Fsx are maximum at inner radius where x is equal to Ri, which is 100 millimeters. The variation of the radial pressure, the hoof stress Fx, and Fsx for different values of x are shown in the form of a graph. The red graph indicates the tensile stress or the circumferential stress or the hoof stress or the tangential stress. So which is 11.4, that is maximum at x is equal to Ri, or the inner surface of the cylinder, and it reduces to 6.4 to become minimum at Rx is equal to R0 or R0, which is the outer radius of the cylinder. The radial pressure, inside pressure is given as 5, outside pressure is not told anything. So therefore, we'll assume that on the outer surface of the cylinder, no pressure is acting, and therefore it is shown as 0.0 for this example. The shear stress variation is obtained, which will come in between, because we numerically add the radial pressure as well as the hoof stress and divide by 2 or multiplied by 0.5 and then obtain the values. These values can be plotted as shown in the yellow color line in the figure. From the graph, it is seen that Px, Fx, and Fsx, they are maximum at the inner radius Ri, and Px at R0 is 0 for this problem, because we assumed that no external pressure is acting on the cylinder. Maximum shear stress is obtained by substituting the values corresponding to x is equal to inner radius, and the values are 11.4 for hoof stress, 5.0 for the radial pressure. So adding it is 16.4 multiplied by 0.5 is 8.2. So which is shown in the graph, yellow color graph. Let us consider another example. A hydraulic cylinder of internal diameter 150 mm contains fluid at a pressure of 55 megapascals. Determine its thickness if the maximum tensile stress in the material of the cylinder is limited to 83 MPa. Tabulate the variation of the radial pressure, hoof stress, and the shear stress across the thickness of the cylinder. As a reminder, circumferential stress is also known as tangential stress or hoof stress or tensile stress, and this is always treated as positive. Similarly, the radial stress is also known as radial pressure, and it is treated as negative. The shear stress is obtained as the mean of the algebraic sum of Fx and Px. Algebraic sum will take care of positive and negative signs carefully. Here we are considering tensile stresses as positive and So the radial stress is also known as radial pressure, treated as negative. Shear stress is half the algebraic sum of the hoop stress and the radial pressure. The given data in this problem is di, that is inner diameter of the pipe, is 150 mm. From this, it is possible to calculate what is the inner radius, which will be used in the Lehm's equations. Inner radius is half the inner diameter. So the inner diameter of the pipe is given as 150 mm. Therefore, the inner radius of the pipe is 75 mm. The outer radius of the pipe can be calculated once we know the inner radius plus the thickness of the cylinder material. So outer radius of the pipe RO becomes equal to 75 plus T. In this problem, we have to determine the T, the thickness of the pipe, in millimeters. Then we can find what is the maximum shear stress, the maximum and minimum values of the hoop stresses, and variation of the radial pressure, the hoop stress, and the shear stress with change in the radius value, which is x. So in the Lehm's equations, for this problem, the given data is Px, the radial pressure, at inner radius is equal to, that is at 75 mm, equal to 55 M.B.A. This is taken from the first formula. Also in this problem, it is given that maximum tensile stress or hoop stress is limited to 83 MPa. This is also at the inner radius, that is at 75 mm. Now, the previous problem, we have used the radial pressure formula 2 times, once for substituting values of the radial pressure at inner surface and outer surface, and we did not use the second formula, which is the hoop stress. In this problem, one value is given, is taken from the radial pressure Px, and another value where the strength of the material is limited to 83 MPa given in the problem is the tensile stress or the hoop stress. So in this problem, we use both the formulas of the Lehm's equations. So substituting Px is equal to 55 MPa when x is equal to 75 mm, we get the formula 55 is equal to B by 75 square minus A. Like that, if we apply Fx is equal to 83 MPa when x is equal to 75 mm, therefore 83 will be equal to B upon 75 square plus A. Now you see, one formula, we have 55 equal to B by 75 square minus A. We can call it as equation 1. And 83 is equal to B by 75 square plus A, which we can call it as equation 2. Now, if you add these two, the plus A and minus A will cancel. 55 plus 83, that becomes 138. B upon 75 square plus B upon 75 square will become 2 times B upon 75 square. So rearranging, B is equal to 138 into 75 square divided by 2. On simplification, the value of B comes to 388,125 and this will be in newtons. Substitute B is equal to 388,125 in equation 1 to get 55 equal to B by 75 square minus A. By rearranging, A becomes equal to 388,125 divided by 75 square minus 55. So on simplification, A becomes 69 minus 55 or A is equal to 14 M.B.A. Now substituting the values of B is equal to 388,125 and A is equal to 14. The Lamb's equations for given problem become Px is equal to 388,125 by x square minus 14. Fx is the root press equal to 388,125 by x square plus 14. Now, at outer radius, we can assume that the radial pressure is 0 because it is not given in the problem. Therefore, we get 0 is equal to 388,125 by R0 square minus 14. By rearranging the terms, we get R0 square is equal to 388,125 divided by 14, or on simplification, R0 square becomes 277 to 3.8. That is, R0 square is equal to 388,125 divided by 14, which becomes 277 to 3.2. Therefore, taking square root, R0 is equal to 166.5 millimeter comes. Also, the outer radius is equal to inner radius plus thickness. Therefore, thickness is equal to R0 minus Ri. Substituting the value of outer radius R0 and inner radius Ri, we get T is equal to 166.5 minus 75, or that is equal to 91.5 millimeters. So this T is nothing but the thickness of the cylinder. Now, the Lamb's equations which are applicable for this particular problem can be written as Px is equal to 388,125 by x square minus 14 and Fx is equal to 388,125 by x square plus 14. So substituting various values of x starting from x is equal to Ri, that is inner radius, up to and including x is equal to Ro, which is outer radius, in increments of I, the values of Px, Fx as well as Fsx, which is the arithmetic mean of the Px and Fx for different values of x, are calculated and they can be tabulated also. So the tabulated results are shown here. So starting from Ri is equal to 75 up to Ry is equal to 166.5. Now here the increment is taken as 15 mm up to 150. Then the outer radius 166.5 is there. So the values of Px and Fx are obtained using the Lehm's formula, which is applicable for this problem, and simplifying, the results are tabulated here correct to 1 decimal place. So from the table, it is seen that both radial pressure Px and hoof stress Fx, they are maximum at inner radius Ri, which is 75 mm here. The corresponding values of radial pressure is 55 MPa and the hoof stress is 83 MPa. The radial pressure decreases to 0 at outer radius and the hoof stress becomes minimum of 28.0 MPa at the outer radius. The shear stress at any radius is again calculated using the formula. They are added to the table by adding one more column where the variation of the shear stress at different radius value x are written down in the fourth column. So the item in the fourth column, the values are obtained by numerically adding the item in the Px column and the Fx column and then dividing the sum by 2. Or multiplying the sum by 0.5. So from the table, it is seen that the radial pressure Px and hoof stress Fx, also the shear stress Fsx, they are maximum at the inner radius where R1 is equal to 75 mm. The values of the variation of the radial pressure Px, hoof stress Fx and shear stresses Fsx for different values of x are obtained are shown in the form of a graph here. The red line corresponds to tensile stress or hoof stress. The blue line is the compressive stress, that is the radial pressure, and yellow color line is the shear stress that varies from maximum at the inner radius Ri to some minimum value at the outer radius R. So from the graph also, it is seen that the values of radial pressure Px, the hoof stress Fx, as well as the shear stress Fsx, they are maximum at the inner radius Ri and we have assumed that the radial pressure at outer radius is 0 as assumed. So maximum shear stress comes at the inner radius. It is 0.5 times 83 plus 55, which amounts to 69.0 MPa. As far as the formula is concerned, we'll write Fi minus Pi, but we have to add them using algebraically, and Pi being negative because it is compressive and Fi is tensile, which is positive. It is necessary to add both the values and multiply the sum by 0.5 or divide the sum by 2. Let us take another example. The inner and outer diameter of a thick cylinder are 250 mm and 350 mm respectively. It is subjected to an internal pressure of 25 MPa and an external pressure of 10 MPa. Show the variation of the radial pressure, hoop stress, and the shear stress across the thickness of the cylinder. Here, this problem, the cylinder is subjected to both internal pressure as well as external pressure. So external pressure was 0 in earlier cases. In this case, there is external pressure of 10 megapascals and internal pressure of 25 megapascals or MPa. So it is a reminder that the circumferential stress is also known as tangential stress or hoof stress or tensile stress, which is treated as positive, and radial stress is known as radial pressure, which is treated as negative. The shear stress is therefore obtained by using algebraic sum of the hoof stress and the radial pressure and multiply the sum by 0.5 or divide the sum by 2. In this problem, inner diameter of the pipe is given as 250 mm. Outer diameter of the pipe is given as 350 mm. Therefore, dividing the values of the diameters by 2, we obtain the radius of the pipe at inside as well as outside. So inner radius of the pipe becomes 125 mm. Outer radius of the pipe becomes 175 mm. The Pi, the internal pressure is given as 25 MPa, and PO, the external pressure, is given as 10 MPa. In this, we have to find the maximum shear stress, maximum and minimum values of the hoof stresses, and the variation of the radial pressure, hoof stress, as well as the shear stress with change in X value. So we'll start with the Lehm's equations, which can be written as Px is equal to B by X square minus A, and Fx is equal to B by X square plus A, where Px is the radial pressure and Fx is the hoof stress at any radius X from the center of the pipe. In this problem, two values of internal and external pressures applied on the cylinder are given. The internal pressure is 25 MPa. This happens at a radius of 125 mm, and the external pressure Px is 10 MPa when X is 175 mm. So these values are substituted separately. That means 2 times, one time for inner radius, another time for outer radius in the first equation. Px is equal to b by x square minus a. So if you substitute Px is equal to 25 MPa when x is equal to 125 mm, therefore 25 is equal to b by 125 square minus a. Px is equal to 25 MPa when x is equal to 125 mm. Therefore, we get 25 is equal to b by 125 square minus a. So Px is equal to 10 MPa when x is equal to 175 mm. This is at the outer radius. By substituting, we get Px, that is 10, is equal to b by x square, where x is 175, so 175 square minus a. Now equation 1 and 2, they contain minus a and minus a. Therefore, if we subtract, the a's get cancelled. So subtract, say, equation 2 from equation 1. So 25 minus 10 becomes 15. And a cancelling, we get b by 125 square minus b by 175 square. Taking b common factor, we get 1 upon 125 square minus 1 upon 175 square. Taking LCM, denominator is 175 square multiplied by 125 square. Numerator, it becomes 175 square minus 125 square. The numerator, you can factorize something like a square minus b square is equal to a plus b into a minus b. Now a plus b means 175 plus 125 becomes 300, and a minus b becomes 175 minus 125 is equal to 50. So 15 is equal to b into 300 into 50 divided by 175 square multiplied by 125 square. Rearranging the equations, b becomes equal to 15 into 175 square multiplied by 125 square divided by 300 divided by 50. Both are 350 are in the denominator. On simplification, we get b is equal to 478,515.6 newtons. Substitute b is equal to 478,515.6 in, say, equation 1, so that we get 25 is equal to b by 125 square minus a. Now, instead of b, we are writing 478,515.6. Substitute this one, getting a is equal to 478,515.6 divided by 125 square minus 25. This simplifies to a is equal to 5.6 MPa. Lehm's equations for given problem therefore become Px is equal to 478,515.6 by x square minus 5.6, and Fx is equal to 478,515.6 by x square plus 5.6. These are the Lamb's equations for this particular problem. Now, comparing the values of B and A of the previous examples, we find that each problem, depending on the given data, the Lamb's equations for the particular problem are to be obtained by using some method like this. Since A and B are two constants, it is necessary to have information sufficient to meet the two conditions, either two values for radial pressure and two values for hoof stress, or one for hoof stress, one for radial pressure, and so on, like that. Substituting values of x now, starting from x is equal to Ri and proceeding up to x is equal to Rho in increments of some I, the values for radial pressure Px, hoof stress Fx, and shear stresses Fsx are obtained, and these things can be prepared in the form of a table. They can be shown. So, values calculated for this problem are listed in this table here. So, from the table you can see at inner radius Ri is equal to 125 mm. The radial pressure Px is maximum, which is 25 M.B.A, and the hoof stress is maximum, which is 36.2 M.B.A for this given problem. So from the table, it is seen that radial pressure, hoof stress, they are maximum at the inner radius Ri. The shear stress at any radius x is given by the formula which we have described 3-4 times now. Now, the radial pressure Px and the hoof stress Fx are to be added algebraically, that is, taking into consideration their plus or minus sign, and the values obtained can be added as another column to the result that is displayed here. So PS is compressive, and therefore negative sign we have to use, and therefore minus of minus becomes plus, and actually we will be adding numerical values and determining the algebraic sum of the radial pressure Px and the hoof stress Fx, and multiplying that sum by 0.5 or dividing by 2 to get the shear stress, which is given in the last column or the fourth column. So from the table, it is seen that all the three, radial pressure Px, hoof stress Fx, and the shear stress Fsx, they are all maximum at inner radius of Ri is equal to 125 mm. The variation of the radial pressure Px, hoof stress Fx, and shear stress Fsx for different values of x obtained are shown in the form of a graph. So in this problem, at the outer radius, the radial pressure is not 0, it is given as 10 MPa. So therefore, there is a difference in the graphs which we have plotted for earlier problems and this problem. From the graph, it is seen that the radial pressure Px, the hoop stress Fx, and the shear stress Fsx, they are maximum at inner radius Ri. For this problem, that Ri is equal to 125 mm and Ry is equal to 175 mm. So maximum shear stress therefore occurs at the inner radius only, and it is calculated as 30.6 M.B.A at inner radius Ri. So you can take down some of these problems as homework and you can try. The inner and outer diameters of a thick cylinder are 160 mm and 220 mm respectively. It is subjected to an external pressure of 5 MPa. Determine the maximum permissible internal pressure if the tensile stress in the material is not to exceed 25 MPa. Show the variation of the radial pressure, hoop stress, and the shear stress across the thickness of the cylinder. So please try to solve this problem using some idea, although this is slightly different from the previous examples, as this particular topic requires some amount of thinking. Therefore, it is cannot be just substituted values of some variables, like determining the area of a circle by substituting given radius, which is the same formula A is equal to pi r square for all problems. In this case, the general form of the Lamb's equation is Px is equal to b by x square minus a, and Fx is equal to b by x square plus a. This general form, we have to convert it into particular form by determining the values of the constants a and b, which are only constants for a given problem only, not constants for all problems. Each problem will have different value of a and different value of b. Therefore, in solving these problems, generally students do not attempt to answer this question because it requires a little bit of thinking. So try to think over, see whether you can solve this problem using the general form of Lamb's equations and using the data given in the problem, which will help in determining the values of the constants a and b for this particular problem. And once the Lamb's equations are determined for this particular problem, then by substituting various values of x, it is possible to calculate the distribution of the radial pressure as well as the hoop stress and also the shear stresses with at different radius values x. In case you are able to solve, you are welcome to send your results to x9t9@yahoo.com. If you do not get the answers correctly, doesn't matter. Next class, we will solve several more problems, which will cover all types of problems that are normally asked in the topic on thick cylinders in not only engineering colleges, but also in polytechnics. Since there are several chapters available in the syllabus as well as in the textbooks, it is not that always a question appears on this. It is by going through several question papers, you will be able to see the pattern of the distribution of the topics in the question paper. So if it appears in the question paper, the marks can vary anywhere between minimum of 8 to maximum of 20, depending on the type of problem and what values are asked. But on an average, most of the question papers will have questions related to thick cylinders to the extent of 10 marks out of the question papers. So anyway, practice this type of problems which involve some amount of thinking will help you to think correctly, clearly, completely, and solve the problem, which takes little more time than pure mechanical substitution of values and simplification, which will be the most of the other topics will have. So therefore, the first to start with, we have taken these thick cylinders so that you will be able to do some amount of thinking to arrive at or converting the general form of the Lamb's equations into the particular Lamb's equations which are applicable to the given problem. Once the Lamb's equations which are applicable for the particular problem is arrived at, then the variation of the various stresses like the radial pressure, the hoop stress, the shear stress, which change in the radius value from the center of the cylinder can be computed as well as plotted in the form of a graph. So please try these problems. If there is any difficulty, let me know. Otherwise, also we will solve more problems in the next session, that will be on 22nd January 2022, Saturday. It is at 6 p.m. to 8 p.m. Starting time is 6 p.m. We'll start sharp at 6 o'clock. Ending time does not matter. We can stop early if something more has to be covered which cannot be completed. We will take up the things which require some extra things in the next class. But if it takes some time to finish the particular problem or the topic, then we can continue that one also. So the video recording of this in an unedited form will be available for viewing any number of times. You are welcome to view. The link will be also sent to all those who have registered so that you can not only view the recording video, you can download it also. Then repeatedly view the same thing as many times as required in individual cases so that the things become more clear, more correct, and more complete. And one day, I repeat, one day you will become an eminent scientist, an eminent professor, an eminent engineer, an eminent innovator in the shortest possible time and in the simplest possible way. See, this one, I actually call it as free offline educational system beyond 2020 or beyond Corona, because the video lesson can be downloaded whenever and wherever free Wi-Fi is available, and once downloaded can be viewed on any video player, including mobiles without SIM card, without constant internet connectivity, or if it is downloaded onto a USB pen drive, you can plug it onto any TV and view the video any number of times. You can pause the video if you want to note down something. You can go back to the rewinding or go back to the previous portions, or you can continue after coming back if you happen to get interrupted while going through or viewing the video lessons. So the important thing is the effort that is made is only to see that the younger generation will get some benefit out of these video lessons. It is because, after all, when we were students, we did struggle spending several sleepless nights to understand the clearly, correctly, completely, spending so many sleepless nights. But we want to make the job easier for the benefit of the younger generations. This is a totally free program. Those of you who are viewing this, if you want to get the you want to participate virtually through Zoom, then please write to x9t9@yahoo.com so that we'll be able to send the link. Otherwise, once you view any one of the video, you'll be able to see all other videos in the series also, and you will be able to go through the lessons correctly, clearly, completely, so that you will become an expert in the shortest possible time and in the simplest possible way.